A colossal stone wall can hide its greatest secret in the seam between two blocks. Our common history celebrates the obvious monuments, but the true signature of ancient genius is etched into the overlooked details. By the end of this exploration, you will see 15 specific features that completely rewrite the story of human innovation. How did builders create chambers that can change your state of mind with sound, or foundations that make stone buildings dance safely through earthquakes? What does it mean when the precision of a 5,000-year-old slab rivals the output of a modern machine shop? We are about to uncover the subtle engineering hidden in plain sight, features that whisper secrets we still struggle to fully understand. This journey redefines technical skill, not as a modern invention, but as a profound legacy coded into stone and earth by sophisticated minds. Are you ready to question everything you thought you knew about the ancient world? The signature of a master is never found in the size of the canvas, but in the brushstroke. For generations, the story of ancient innovation has been told through the scale of its monuments, the pyramids, the temples, the sprawling cities. We stand in awe of their sheer presence, their endurance. Yet this focus on the grand finale of construction has, until recently, quietly overlooked the prologue written in the workshop. The real revolution in understanding begins when we stop asking what they built and start asking how they thought. The technical skill we are about to explore exists not in the towering walls themselves, but in the millimeter gap between them. Not in the weight of a multi-ton block, but in the precise angle cut to bear that weight for millennia. These are the features that required a deep, intuitive grasp of forces that science would not formally name for thousands of years. They applied principles of material stress, acoustic resonance, and celestial geometry without a single textbook or formal equation. As space archaeologist Dr. Sarah Parcak notes, the true marker of an advanced society is found in the quiet consistency of its everyday engineering, the repeatable solution to 1,000 invisible problems. This shift in perspective transforms an ancient site from a static museum piece into a dynamic conversation. Each precise joint, each cunning drainage channel, each acoustically tuned chamber is a fossilized thought, a permanent record of a problem identified and elegantly solved. When we examine these 15 overlooked features, we are not merely cataloging architectural trivia. We are decoding a lost language of practical physics and material science. We are peering over the shoulder of the ancient engineer at their drafting table, watching them translate abstract mathematical relationships into solid, enduring stone. And this raises a profound, tantalizing question. Could there be a common thread of problem-solving, a shared intellectual toolkit that connected cultures who supposedly never met? To find that thread, we must start with a feature so fundamental, so perfectly executed, that it has literally supported civilizations from the ground up. The foundation of all great engineering is not in the block but in the bond. High in the thin air of the Peruvian Andes, the fortress of Sacsayhuamán presents a first, breathtaking lesson in this principle. To the casual eye, it is a formidable wall of colossal gray stone, but step closer and the wall transforms. It reveals itself not as a stack of giant bricks, but as a single, continuous sculpture, a monumental three-dimensional jigsaw puzzle where no two pieces are alike. The stones, some weighing well over 100 tons, boast dozens of intricate angles and facets, each one carved to mate perfectly with the unique contours of its neighbors. This is the pinnacle of ashlar masonry, and its genius is invisible. The technical marvel is not the sheer mass they moved, though that is astounding. It is the precision with which they shaped these polygonal giants to lock together without a single drop of mortar. Think of it not as a wall, but as a system. During one of the region's frequent earthquakes, a rigid, mortared structure would crack and crumble under the shifting forces, but this interlocking puzzle is designed to dance. When the ground trembles, the stones in a Sacsayhuamán wall can shift and settle minutely against one another, dissipating the energy through friction along their many complex joints, then settling back into place. They are a lesson in flexibility written in granite. This creates an almost impossible problem for the builders. Each irregular block had to be individually measured, its future neighbors assessed, and its faces painstakingly shaped to create that perfect, airtight fit. This was not a matter of rough hammering. It required a sophisticated, almost intuitive grasp of geometry and structural load distribution, understanding exactly how the weight of the mountain above would flow down through each unique interface. The process would have demanded not just skill, but relentless patience, involving endless cycles of test fitting, fine carving, and adjustment. The result is a wall that has shrugged off centuries of seismic violence, its stability a direct function of its intricate, hidden joinery. This single feature forces us to confront a haunting question. What tools or methods did they possess that allowed for such precision working on such an immense scale? The idea of artisans with simple bronze chisels and stone hammers achieving these flawless, complex joints on granite boulders strains belief. It has fueled lasting speculation about lost knowledge, perhaps a method to temporarily soften stone, or a cutting technique far more advanced than our standard histories allow. The walls of Sacsayhuamán stand less as a barrier and more as a permanent challenge to our assumptions about ancient capability. And if they could master the union of stone on such a grand scale, what then could they accomplish with the marriage of earth and water? Sound itself can be carved from silence given the right shape of stone. Far from the Andean peaks, on the green, mist-shrouded island of Ireland, lies a monument of a different kind of genius. Newgrange is a massive, circular passage tomb, a structure older than both Stonehenge and the Great Pyramids of Giza. For decades, its fame rested on a single, spectacular solar alignment, where the winter solstice sunrise pierces a roof box to illuminate the inner chamber. But this ancient marvel holds another, more intimate secret, one not of light but of sound. Step inside the narrow, stone-lined passage and into the central chamber, a space capped by a soaring corbelled roof where each layer of stone gracefully overlaps the one below. The air feels different here, thick and still. If you were to speak or to hum a low tone, you would notice something extraordinary. The chamber does not just echo your voice, it transforms it. The space seems to gather the sound, to hold it, and amplify it into a deep, resonant hum that vibrates through your very bones. This is no accident of construction. Archaeoacoustic research, which studies the sound properties of ancient sites, has revealed that Newgrange's builders crafted this chamber with precise dimensions and specific stone placements to create a powerful, resonant frequency. In essence, they built a giant stone instrument. For the people who gathered here over 5,000 years ago, likely for ceremonies of remembrance and connection, the effect would have been profound. The steady rhythm of a drum or the unified chant of voices would not merely be heard, it would be felt, filling the confined space with an overwhelming physical presence. Researchers suggest such sustained, low-frequency resonance can subtly alter brainwave patterns, potentially facilitating states of focused meditation or heightened communal experience. This implies a staggering depth of ancient knowledge. These Neolithic builders possessed an empirical, hands-on understanding of how sound waves behave, how they reflect off certain surfaces, and how the geometry of a space can trap and amplify specific frequencies. They were manipulating sensory experience through architecture, using technical skill to engineer a spiritual atmosphere. This feature completely redefines the tomb. It is not just a resting place for the departed, it is a resonant vessel for the living, a tool designed to bridge the perceived gap between the physical and the metaphysical. The precision required to achieve this acoustic effect while also maintaining the structural integrity of a corbelled roof speaks to a holistic mastery where physics and purpose were inseparable. At Newgrange, the stones do not just mark a sacred space, they actively participate in the ceremony, turning architecture into a living, breathing component of ritual. This mastery over the intangible forces of sound and space makes the next feature, born from a need to master the very tangible force of water, all the more compelling. Water is a civilization's lifeblood, and its control is the ultimate test of engineering foresight. While the resonant chambers of Newgrange manipulated an intangible force, the Minoans of ancient Crete tackled a far more immediate challenge, mastering the physical flow of water with a chemical innovation that would not be widely rivaled for over 1,000 years. At the heart of the sprawling palace of Knossos, beneath the vibrant frescoes and grand courtyards, lies a hidden network of sophisticated plumbing. Here, artisans did not just channel water, they invented the very material to contain it. They developed a unique hydraulic cement, a brilliant precursor to the later Roman concrete, specifically designed to set and harden underwater. This was no simple mortar. Its durability came from a deliberate, chemically savvy formulation, mixing slaked lime with a fine volcanic ash found locally. When combined with water, these ingredients undergo a pozzolanic reaction, creating a crystalline bond that is not only incredibly strong but also completely resistant to water penetration. The technical skill here is profound. It required an empirical understanding of material properties, a consistent recipe, and a production process reliable enough to line entire aqueducts and seal large cisterns. This was chemistry and civil engineering working in concert. The result was a resilient, waterproof infrastructure that managed fresh water supply and waste removal with an efficiency that would be admirable in any pre-industrial city. This innovation speaks to a society thinking on a systemic, urban scale. It provided not merely royal convenience but public health, controlling the environment to prevent illness and improve quality of life. The longevity of these installations, still evident today, is a testament to a mastery that was both precise and scalable. The Minoans were not just reacting to their environment, they were proactively shaping it with applied science, solving the practical problems of dense communal living through material innovation. This command over chemistry and flow hints at a mind looking for patterns, for predictable reactions in both material and nature. It begs a compelling question: if they could engineer the behavior of water and stone, what other patterns in the world around them might they have sought to codify and predict? Perhaps even the most reliable pattern of all, the unwavering journey of the sun and stars across the sky. A machine leaves a different kind of fingerprint than a human hand. Scattered across the windswept Bolivian Altiplano, the ruins of Puma Punku look less like a building and more like a factory floor after a cataclysm. Giant stone blocks, some weighing many tons, lie shattered and dispersed as if by a colossal force. Among this debris are the real mysteries, flat slabs and intricate H-shaped connectors made from andesite, a stone as hard as granite. On their surfaces, you find features that simply do not belong. There are long, ruler-straight grooves cut with a crisp, clean edge, channels so uniform in depth and width that they maintain millimeter-perfect consistency along their entire length. There are perfect circular drill holes that plunge deep into the stone with parallel sides, and surfaces so flat and smooth they could be mistaken for modern machine shop output. The technical skill here is not about moving mass, it is about controlling material removal with inhuman consistency. These are not the rough, chiseled marks of a craftsman with a hammer. They are the signatures of a process. The precision of these grooves suggests the use of a guided, repeating mechanism. Imagine a cutting tool mounted on a fixed track, able to make pass after identical pass along the stone's surface, a concept akin to a primitive milling machine or a saw with a jig. This implies something revolutionary: standardization. It points to a manufacturing mindset where components were not individually sculpted works of art, but precisely replicated parts designed to fit together in a modular assembly system. The purpose of these flawless grooves and holes is still debated by researchers, with leading theories suggesting they held now missing metal clamps or served as registration points for aligning massive blocks. But the how is what truly redefines the site. To achieve this on andesite requires more than patience. It requires technology capable of exceeding the material's hardness. The absence of any known contemporary tools that could perform such work forces a profound reconsideration. It suggests the Tiwanaku culture, which flourished here over 1,000 years ago, possessed a highly specialized industrial technique, a method of cutting and shaping hard stone that has since vanished from the historical record. Puma Punku's legacy is not in a completed structure, but in these scattered components, each one a fossilized instruction from a lost assembly manual. They whisper of a workshop where geometry was enforced not by the eye, but by a tool where the goal was not just to build but to produce. If such precise, repeatable manufacturing was possible in the highlands of ancient Bolivia, it compels us to look for similar fingerprints elsewhere, perhaps in a place where the builders chose to leave their most intricate work not on the surface, but hidden forever in the dark. The most resilient structure is one that knows how to sway. In the highlands of northern Ethiopia, the medieval builders of Lalibela performed a kind of architectural magic, carving 11 spectacular churches not from blocks of stone, but directly down into the living bedrock of a mountainside. These are not buildings placed upon the earth, they are buildings liberated from it. The most iconic, Beted Georgis, shaped like a perfect Greek cross, sits at the bottom of a deep, square quarry. To stand before it is to witness a miracle of subtraction, as if a giant hand reached down and sculpted a church from a single, colossal piece of stone. But the true genius of Lalibela is not visible to the admiring eye. It lies beneath the foundation, in what the stone carvers deliberately chose not to remove. As they painstakingly excavated the volcanic tuff around and underneath each monolithic church, they left behind a thin, continuous cushion of the original bedrock. This was no oversight, it was a masterstroke of seismic engineering. This cushion acts as a natural isolation pad. When the ground shakes during one of the region's frequent earthquakes, the solid rock church is not rigidly locked to the trembling earth. Instead, it can rock and shift minutely on this carved stone cushion, its immense weight allowing it to move as a single, unified mass. The energy of the tremor is dissipated through this gentle, controlled movement, sliding across the interface rather than traveling up into the structure to create catastrophic shear cracks. This is the ancient, intuitive principle of base isolation, a technique that forms the cornerstone of modern earthquake-resistant design for skyscrapers and bridges today. The foresight this required is staggering. These artisans were not just sculptors, they were geologists and dynamicists. They had to understand the properties of their material intimately, predicting how the monolithic mass would behave under stress. They executed this plan while carving from the top down, a dizzying process that required them to visualize the final, freestanding structure and its hidden supports while still surrounded by solid rock. Every strike of the hammer had to be an act of faith in an unseen future stability. This feature represents a philosophy in stone, a profound harmony between human creation and natural force. The builders of Lalibela did not seek to conquer the earth with an immovable object. Instead, they engineered a graceful partnership, allowing their sacred architecture to dance lightly on the very land that gave it form. This respectful dialogue with natural forces preserved these churches through centuries of seismic activity, a quiet testament to a technical skill that understood motion as well as monument. And if ancient minds could engineer structures to move with the earth, what other fundamental forces might they have sought to harness? Perhaps even the invisible but undeniable force that guides a compass needle. The ground itself had to be made perfect before a single stone could rise. The Great Pyramid of Giza is a monument defined by its staggering height and mass, a symbol of scale burned into human memory. Yet its most profound technical statement is not vertical but horizontal. Before the first of the 2.3 million blocks was set, the builders of the Fourth Dynasty performed a feat of foundational engineering that remains almost incomprehensible. They prepared a 13-acre limestone foundation platform, an area equivalent to over 7 modern football fields, and they leveled it, not roughly, not approximately, but to a flatness within just 2.1 centimeters. To put that in perspective, if you placed a regulation soccer ball on one corner of the pyramid's base, the variation across the entire city block-sized foundation would be less than the height of the ball itself. This is a precision that rivals projects built with laser-guided grading systems and digital theodolites. Achieving this on the Giza Plateau, with its natural slopes and uneven bedrock, was the first and perhaps most critical engineering puzzle. How did they establish a true horizontal plane across such a vast expanse without modern instruments? Researchers propose several ingenious methods rooted in simple, observable physics. One leading theory involves the use of water. By digging a grid of shallow trenches across the site and filling them with water, they could have created a perfectly level network of mirrors reflecting the sky. The surface of still water always finds true level, and by marking consistent heights along the trench walls, they could have transferred that horizontal datum across the entire construction zone. Another possibility involves the systematic use of shadow-casting poles or sighting instruments over long distances, using the sun's path to check for deviations. Whichever method they used, the outcome demonstrates a systemic, project-wide philosophy of extreme accuracy. This foundational flatness was not an aesthetic choice, it was a structural imperative. The pyramid's immense weight, estimated at nearly 6 million tons, had to be distributed perfectly evenly to prevent catastrophic settling or shear forces from tearing the monument apart from its base upward. A discrepancy of even a few degrees in the foundation would have been magnified exponentially with each ascending course, causing the entire structure to lean or collapse long before completion. Furthermore, this perfectly level plane was the essential canvas upon which the pyramid's legendary astronomical alignments were drawn. The near-perfect cardinal orientation of its sides to true north, south, east, and west relied first on this flawlessly flat starting point. This single, overlooked feature forces a complete rethinking of the project. It reveals that the pyramid's wonder is not merely in its culmination, but in its conception. It speaks of a managerial and technical mindset that understood the absolute necessity of getting the first step impeccably right, because every single step that followed depended upon it. The builders were not just stacking stones, they were executing a precision multi-year project with a tolerance that would challenge modern engineers. This foundational mastery provided the stable, silent stage for everything that came next, a testament to a skill that understood that true greatness is built from the ground up with patience and phenomenal exactitude. And if such control could be exerted over the earth itself, what then could be achieved when the goal was not stability, but the creation of impossible, gravity-defying space? A city's greatness is measured not by its grandest temples but by its quietest channels. While the pyramids mastered foundational flatness, another ancient civilization turned its genius to a far less glamorous, yet utterly vital, challenge: managing what 1 million people leave behind. Rome's legendary Cloaca Maxima, the greatest sewer, is often remembered for its colossal scale, a brick-lined tunnel large enough for a man to stand upright and even guide a boat through. But its true, enduring brilliance is not in its size, it is in its subtlety. The engineers of the Roman Republic, and later the Empire, designed this subterranean river with a masterful understanding of an invisible force, the consistent, unrelenting pull of gravity. They carved and laid the channel with a meticulously calculated gradient, a gentle, unwavering slope that ran for miles beneath the bustling streets. This was not a steep chute, but a carefully calibrated incline, just enough to ensure that water and waste would flow continuously toward the Tiber River, never stalling long enough to create a catastrophic blockage. This self-cleaning design was a triumph of long-term hydraulic thinking. It meant the system could function for centuries with minimal intervention, using the natural movement of water to perpetually scour its own walls. But the engineers did not stop with flow. They understood that a stagnant, enclosed space breeds more than just inconvenience. At strategic intervals along the sewer's course, they incorporated access shafts, openings that served a dual and ingenious purpose. First, they allowed for essential maintenance, providing points where workers could descend to clear the rare obstruction. Second, and perhaps more critically, these shafts acted as ventilation ducts. They allowed fresh air to circulate through the tunnels, preventing the buildup of dangerous, flammable gases like methane, which could asphyxiate workers or even explode. This combination of gradient and ventilation represents a holistic, almost modern approach to civil engineering. It was infrastructure designed with foresight, addressing not just the immediate problem of waste removal, but the ongoing challenges of public health, environmental management, and worker safety. The Cloaca Maxima was not merely a construction project, it was a systemic solution for urban living. Its effectiveness was so profound that sections of this original system, conceived over 2,500 years ago, still form part of the drainage network beneath modern Rome. This feature redefines Roman technical skill, showing it was as much about the patient, precise calculation of a slope and the thoughtful placement of an air shaft as it was about erecting majestic arches. It was engineering in service of everyday life, a quiet, underground testament to the idea that a civilization's longevity depends as much on what it removes as on what it builds. And if ancient minds could engineer such resilience beneath their feet, what astonishing feats of connection might they have achieved when looking to the horizons beyond their city walls? Stone can become a library, its pages open to the sky. High on the arid Bolivian Altiplano, not far from the enigmatic rubble of Puma Punku, stands a monument of a different order. The Sun Gate of Tiwanaku is a single, massive block of andesite, carved into the form of a monumental doorway. To the untrained eye, it is a stunning piece of ancient art, covered in a complex frieze of winged figures and intricate patterns. But this is where the true skill lies, hidden in plain sight. The gate is not a passage for people, it is a portal for light and knowledge, a sophisticated astronomical instrument and calendar carved in enduring stone. The central figure, often interpreted as a solar deity, is surrounded by 48 squares, each containing a unique winged attendant. Researchers studying the alignments have proposed that this iconography functions as a precise symbolic code. The positions and groupings of these figures are believed to map onto the solar year, marking the solstices and equinoxes with specific elements of the design. But the ambition may reach even further. Some analyses suggest the patterns could also track the more complex 18-year cycle of the lunar standstill, the point where the moon reaches its extreme northern and southern rise and set points on the horizon. This implies a staggering depth of long-term celestial observation. The technical skill here is threefold. First, there is the masterful stoneworking. carving this complex code into unforgiving andesite with flawless clarity that has survived over a millennium of exposure. Second, and more profound, is the astronomical knowledge itself, the product of generations patiently recording the slow dance of heavenly bodies, distilling patterns of time into a symbolic language. Third is the intentional placement, the gate positioned so that on specific, crucial days of the year, the rays of the rising or setting sun would strike particular carved elements, illuminating them like a cosmic spotlight confirming the date. This transforms the gate from a static sculpture into an interactive device. It represents the ultimate integration of skill sets, cosmology, art, and engineering fused into a single functional object. This feature completely redefines the scope of ancient technical achievement. It shows that their mastery extended beyond manipulating the physical world into the realm of information technology. The Sun Gate is a durable database, a permanent stone archive for tracking time and predicting celestial events, essential for organizing agriculture, ritual, and the very rhythm of society. It is proof that for these ancient astronomers, the sky was not a mystery but a readable text, and they possessed the technical skill to inscribe its lessons for eternity. This desire to capture and utilize celestial knowledge in architecture suggests a mind looking for harmony between heaven and earth, a pursuit that would find one of its most perfect and mysterious expressions in a garden of towering stones on a windswept English plain. The health of a city is written in the pipes its residents never see. While Rome mastered the grand scale of waste removal, another civilization, flourishing over 4,000 years ago along the banks of the Indus River, engineered a different kind of safeguard, one that worked on a microscopic level. In the meticulously planned cities of Mohenjo-Daro and Harappa, archaeologists uncovered something remarkable in the quiet corners of everyday life. Nearly every home, from the most modest dwelling to the grander structures, contained a private bathroom, complete with a sophisticated drainage system that channeled wastewater out into covered street sewers. But the true innovation was not just in the network itself, it was in the lining. These bathrooms and drains were not simply carved from brick. They were carefully plastered with a smooth, durable coating made from a specific material, gypsum. This was a deliberate, intelligent choice. Gypsum plaster possesses a subtle but powerful quality. It is naturally antimicrobial. The chemical composition of this processed material creates an environment that actively inhibits the growth of bacteria and mold. In the warm, humid climate of the Indus Valley, where standing water in drains could quickly become a breeding ground for illness, this feature was a silent guardian. The technical skill here is multifaceted and profound. First, it required the empirical discovery of gypsum's hygienic properties. Someone, long ago, had to observe that surfaces treated with this plaster stayed cleaner, smelled fresher, and perhaps were associated with better health outcomes. This was early material science in action. Second, it demanded the development of a consistent production process, mining the raw gypsum, calcining it to create plaster, and mixing it to a workable consistency. Finally, and most impressively, it involved the systematic application of this knowledge across an entire civilization. This was not a royal luxury, it was a standardized urban feature. The consistent use of this plaster in countless private homes and public drains points to a shared civic understanding, a communal commitment to sanitation that was baked into the very infrastructure of the city. This represents a proactive, rather than reactive, approach to public health. It shows a society thinking holistically about the challenges of dense urban living, applying technical solutions not just to move water, but to purify the environment at the point of contact. This quiet, pervasive innovation speaks to a sophistication that rivals the more visible monuments of other ancient cultures. It tells us that for the people of the Indus Valley, technical skill was measured not only in what they built to impress the gods, but in what they built to care for one another. It was engineering with a profound sense of communal welfare, a legacy written not in towering stone, but in the smooth, clean lining of a humble drain. If such thoughtful engineering could be directed toward the flow of water and the prevention of unseen threats, it makes you wonder what other invisible forces they might have sought to understand, perhaps even the mysterious force that allows a massive stone door to pivot on a pinpoint with the gentle push of a single hand. The true mastery of water lies not in stopping its flow, but in directing its dance. In the lush Sichuan basin of China, a symphony of irrigation has been playing continuously for over 2,300 years, a testament to an engineering philosophy that saw nature as a partner, not an adversary. The Duzhongyan system, conceived during the Qin dynasty, solved a perennial and devastating problem: the Min River's violent seasonal flooding followed by crushing drought. But its builders, led by the visionary administrator Lai Bing, rejected the obvious solution of building a massive dam to forcefully restrain the river. Instead, they chose a path of profound subtlety and intelligence. They engineered a diversion using the river's own power to guide it. At the heart of this living system were its sluice gates, devices of elegant simplicity and genius. These were not heavy wooden barriers lifted by straining teams of laborers. They were dynamic components built from bamboo cages filled with stones, creating adjustable counterweights. By adding or removing stones from these cages, operators could finely tune the gate's resistance, allowing precise volumes of water to flow into the intricate network of irrigation channels that fed the farmland below. This was a self-regulating mechanism. In the rainy season, higher water pressure would automatically push the gates open wider to prevent flooding upstream, while in the drier months, the weighted gates would settle, conserving water for the channels. This design required a deep, intuitive grasp of fluid dynamics and leverage, understanding exactly how much force moving water exerts and how to balance it with a calibrated mass. The entire system was a masterpiece of ecological engineering. It included a cleverly placed dividing levee shaped like a fish's mouth to split the river, and a spillway channel designed to flush out silt and sediment, keeping the system from clogging. There were no concrete monoliths battling the current, only intelligent interventions placed in harmony with the river's natural topography and behavior. The technical skill here was not one of domination, but of orchestration. It was applied to create a sustainable, self-correcting relationship between human need and natural force. Duzhongyan did not just water crops, it created stability and prosperity for millions, and it continues to do so today, a functional monument to the idea that the most advanced technology is often the one that leaves the lightest, most respectful footprint. This ancient principle of working with nature rather than against it stands as a strikingly relevant lesson for our own modern environmental challenges. It proves that longevity is engineered through harmony, a concept that finds a curious echo in another ancient structure, one designed not to manage water, but to defy another relentless force, the sheer crushing weight of the earth itself. Perfection is not a straight line, but a gentle curve. Crowning the Acropolis in Athens, the Parthenon stands as the ultimate symbol of classical harmony, its rows of marble columns appearing flawlessly straight, vertical, and balanced to anyone gazing up from below. Yet this impression of perfect rectilinearity is one of history's most beautiful deceptions. The temple's base, the stylobate, does not lie flat. Its long sides curve subtly upward at the center, rising nearly 7 centimeters over their 70-meter length, while the shorter sides follow suit. This convex bow is mirrored in the entablature, the horizontal structure above the columns. To the naked eye, these lines are straight, but a laser level or a taut string would reveal the elegant, intentional arc. This was no construction error, but a masterful correction. The builders understood a quirk of human perception, that the eye, when scanning a long, uninterrupted horizontal line against an open sky, will perceive it to sag or dip in the middle. To preempt this optical illusion and create the visual experience of perfect flatness, they built the curve in. The technical skill required to execute this is staggering. Every single one of the 46 outer columns had to be uniquely crafted. Not only were they slightly tilted inward for stability, but their heights varied minutely, and the circular drums that stacked to form each column had to be cut with subtly tapered edges to follow the curve of the structure above and below. Each of the thousands of blocks in the entablature was a custom piece, its bottom and top surfaces cut at precise, non-parallel angles so they would all meet seamlessly along the invisible arc. This was projective geometry and perceptual psychology applied on a monumental scale, requiring both a mathematical model of the entire structure and the artisan's touch to realize it in marble. It represents a fusion of disciplines we rarely associate with the ancient world, where the architect was also a cognitive scientist, engineering not just a building, but the viewer's experience of it. They were manipulating perception to create an ideal of majesty that pure geometry could not achieve. This hidden curvature redefines the Parthenon from a static monument into a dynamic interaction between stone and site, a testament to builders who knew that true technical mastery meant accounting for the frailties of the human eye. It prompts a fascinating question: if they could engineer such subtlety into a temple meant to be seen, what astonishing complexity might they have hidden in structures meant to be sealed away forever, in the silent, weightless dark beneath a mountain of stone? Stone can be melted, and ancient walls bear the scars of impossible heat. Perched atop hills across Scotland, from Tap O Noth to Dunadir, lie the enigmatic remains of Iron Age forts with a startling secret. Long sections of their drystone ramparts are not merely blackened by fire, but utterly transformed. The very rock has been fused into a brittle, glass-like substance, a process known as vitrification. This is not a surface scorch, it is a fundamental metamorphosis of the stone itself, requiring sustained temperatures well over 1,100 degrees Celsius. To put that in perspective, a typical wood fire burns at roughly half that heat. Achieving such an extreme temperature across a massive, exposed wall section, especially in the damp Scottish climate, presents a technical puzzle that has resisted clear explanation for centuries. The skill, or perhaps the mystery, lies in the method. How could ancient builders generate and contain a furnace-like heat against a sprawling stone rampart? Some researchers point to evidence of intense, deliberate burning, suggesting the walls might have been packed with timber lattices and fuel, then set ablaze in a controlled configuration to literally weld the stones together, creating a stronger, monolithic defensive barrier. This would imply a pyrotechnic mastery, a deliberate recipe of stone, wood, and airflow engineered to trigger a ceramic transformation. Others propose these vitrified sections are the catastrophic result of defensive sieges, where enemy attacks set the timber-reinforced walls ablaze with such ferocity that the stone itself melted. Yet even this theory requires a phenomenal and sustained conflagration, a firestorm of specific conditions to achieve vitrification rather than simple collapse. A more speculative line of inquiry wonders if this effect hints at a lost high-temperature process, a specialized knowledge of using certain fuels or mineral additives to drastically lower the melting point of local stone. Whatever the cause, the outcome stands as a stark physical anomaly. These glassy ramparts are a permanent record of an extreme thermal event, a snapshot of ancient fire wielded on an industrial scale. They force us to confront a gap in our understanding of prehistoric material science. Were these builders not just stacking stone, but actively altering its very molecular structure through controlled combustion? The vitrified forts resist a single, comfortable answer, holding both the possibility of intentional technical skill and the shadow of a destructive power so great it left the landscape permanently changed. In their glazed, silent surfaces, we see the line between construction and alchemy blur, a reminder that some ancient achievements were forged not just with tools but with flame. The strength of an empire is measured in the length and resilience of its lifelines. While the Roman aqueducts carried water, their legendary roads carried something far more vital, the very momentum of the state itself. We all know the iconic image, those impossibly straight lines cutting across the landscape. But the true engineering marvel of a Roman road was not its direction, it was its depth. The genius was buried, a meticulously crafted, multi-layered foundation called the agger. This was not a simple path beaten flat by countless feet. It was a modular, manufactured product, a sophisticated sandwich of materials designed to conquer time and traffic. The process began with the excavation of a wide trench, often over a meter deep. Into this trench, Roman engineers would lay a carefully sequenced strata. First, a stable foundation layer of packed sand or sometimes a rudimentary mortar, the pavimentum. Upon this, they placed a thick middle course of coarse gravel or crushed stone bound with clay, the rudus. Finally, the crowning surface was a layer of interlocking polygonal stones, meticulously fitted together, known as the summum dorsum. Each layer had a specific, intelligent purpose. The sand base provided drainage, preventing water from softening the ground beneath. The gravel layer acted as a shock absorber, distributing the immense weight of carts and marching legions. The top stones offered a durable, slightly cambered running surface that shed rainwater to the roadside ditches. But the true technical skill was not in building one perfect road. It was in replicating this complex recipe across thousands of miles, from the rain-soaked highlands of Britannia to the arid deserts of Syria. This was a standardized, scalable formula for infrastructure. Surveyors, the agrimensors, would plot the route, and then teams would execute the same layered construction process, adapting only the locally available materials while adhering to the core engineering principles. They were applying a systems approach to civil engineering, creating a network where any section, anywhere in the empire, could be expected to perform with the same legendary durability. This modular precision transformed logistics. It meant legions could march in all weather, supply wagons could roll year-round, and communication could flow at unprecedented speed. The roadbed was the unseen engine of imperial cohesion, a triumph of applied geology and project management. It demonstrates that technical skill reaches its zenith not merely in a single masterpiece, but in the creation of a repeatable, reliable process that can be stamped across a continent, turning ambition into enduring stone and gravel. This mastery over terrestrial connection makes the ambition of the next feature all the more breathtaking, for it involves a structure that sought not to traverse the Earth, but to capture the cosmos in a single, silent alignment. A sanctuary's power can be shaped by the hollows within its walls. Within the soaring domes and thick masonry of many Byzantine and early Christian churches, builders concealed a quiet acoustic secret. As they constructed the walls and the great curved ceilings, they carefully embedded large, empty clay pots or amphorae into the fabric of the building itself. These were not structural supports or storage containers, but finely tuned instruments. Their purpose was to capture and transform sound, acting as primitive but highly effective Helmholtz resonators. This principle, named for a 19th century physicist, describes how an enclosed volume of air in a cavity with a narrow opening can vibrate at a specific, natural frequency. In the context of these sacred spaces, the clay pots were precisely sized and shaped to resonate with the fundamental tones of the human voice, particularly the deep, sustained notes of liturgical chant. The technical skill here is beautifully subtle. The builders had to understand that the architecture itself could be an active participant in the ritual. They were not just creating a room to contain sound, they were engineering the very quality of that sound. Each vessel, with its specific internal volume and neck opening, was designed to absorb certain muddying echoes and selectively amplify the clarity of spoken and sung prayer. This required careful calculation during the planning phase. The masons had to determine the correct size for the pots, their optimal placement within the complex curvature of a dome or along a resonant wall, and the precise number needed to achieve the desired acoustic effect across the entire congregational space. All of this had to be orchestrated during the messy, demanding process of masonry construction, with the fragile vessels positioned and then permanently entombed in mortar and stone. This feature represents an applied science of atmosphere. It shows a culture thinking holistically about the sensory experience of worship, using material innovation to bridge the gap between the human voice and the divine. The auditory environment was not left to chance. It was consciously composed with clay and geometry, ensuring that every word and every note reached the farthest corner of the church with enhanced purity and presence. This ancient mastery of resonance, of shaping intangible waves of sound with fixed vessels of earth, stands as a profound testament to a technical skill that sought perfection not just in sight, but in hearing. It completes a fascinating arc in our journey, from chambers that altered consciousness with sound to walls that purified prayer with hidden parts. Yet it compels one final, overarching question. If these diverse cultures, separated by continents and millennia, could each develop such sophisticated, niche solutions to complex problems of physics and perception, what does this tell us about the shared trajectory of the human mind when confronted with a challenge? The final overlooked feature offers a lesson in architectural humility, a structure that bows to the very element it was built to contain. Across the arid plains of Western India, the magnificent stepwells, like the breathtaking Chand Bayori, descend into the earth like inverted palaces. With over 3,500 symmetrical steps cascading down 13 stories to a dark, placid pool, they appear as temples to geometry and shadow. Yet their true genius is not in their stunning visual symmetry, but in their profound dialogue with an invisible force, the seasonal rhythm of the groundwater itself. These were not simple holes in the ground, but sophisticated, self-regulating public utilities, engineered to accommodate the dramatic annual dance of the water table. The technical skill began long before the first stone was laid with precise hydrological surveying. Builders had to locate not just water, but a reliable aquifer whose level would fluctuate predictably between the monsoon rains and the parching dry season. This required a deep, localized understanding of subterranean geology, reading the landscape to predict the behavior of hidden water. Once the site was chosen, the architectural design performed a masterful balancing act. The intricate staircases and tiered galleries were not merely for dramatic descent, they were a functional interface. Each step, each landing, provided stable access to the water's edge no matter how high or low it rested within the cavernous space. As the water receded in the dry months, the community could simply descend further, following the life-giving resource down the architectural spine built to anticipate its retreat. Simultaneously, the massive subterranean form created a natural climate control system. The vast, shaded interior and the large surface area of the water promoted evaporative cooling, dropping the temperature within the well significantly below the scorching heat above. This transformed the stepwell into a vital social sanctuary, a cool, communal living room where people could gather, work, and find respite. All of this was achieved while solving a formidable structural puzzle, building such a colossal excavated void in often unstable, sandy soil. The builders employed techniques like stepped retaining walls and cleverly distributed loads to prevent the earth from collapsing inward, a testament to their mastery over both form and foundation. Chand Bayori and its counterparts were, therefore, the ultimate fusion of utility and beauty, of civil engineering and community space. They managed a scarce, vital resource with elegant efficiency, showcasing an intuitive, almost poetic understanding of natural cycles. They did not fight the environment, they adapted to it, creating a resilient architecture that moved in harmony with the Earth's own breath. This quiet, profound skill brings our journey to a close, not with a shout of triumph, but with a whisper of wisdom. From earthquake-dancing walls to resonating chambers, from self-cleaning sewers to these water-leveling wells, a common thread emerges. Ancient technical skill was not about imposing human will upon the world through brute force. It was about observing natural patterns with exquisite care, understanding material properties with intimate hands-on knowledge, and then designing elegant, enduring solutions that worked in concert with those very forces. These 15 overlooked features are not anomalies, they are a legacy. They remind us that innovation is often hidden in the details, in the thoughtful response to a fundamental human need. They challenge us to look beyond the monument and to see, in the quiet joinery and the intentional curve, the true signature of a master. The true measure of these 15 marvels is not in their isolation, but in the pattern they form together. From the seismic isolation pads of Lalibela to the acoustic clay vessels of Byzantium, they weave a tapestry of ancient technical skill that is both wonderfully diverse and profoundly sophisticated. This is not a story of a single genius or a lone invention, but of countless minds across continents and centuries, arriving at elegant solutions to the universal human challenge of building a life within a complex world. They sought shelter from the shaking earth, clean water for their cities, sound to elevate their ceremonies, and structures to align with the cosmos. In every case, their answer was not brute force, but a deep, patient conversation with the materials and forces at hand. This exploration quietly redefines our view of ancient civilizations. They were not primitive societies merely struggling for survival, but ingenious communities of problem solvers. Theirs was a mastery born of relentless observation and hands-on experimentation, an empirical knowledge passed down through generations of craftspeople who learned to read the grain of stone, the flow of water, and the path of light. Their legacy is one of applied wisdom, where every precise joint and calculated slope represents a moment of profound understanding made permanent. As the archaeologist Louis Binford once reflected, technology is the socialized knowledge of how to use tools and resources. These features are the ultimate expression of that idea, knowledge solidified into form, a silent language of resilience and creativity coded into the very landscape. That coded wisdom still surrounds us, waiting to be read with fresh eyes. It invites a deeper curiosity, a willingness to look past the grand facade and appreciate the subtle, brilliant details that made the facade possible. It asks us to see the ancient world not as a museum of static artifacts, but as a living archive of human ingenuity, where every overlooked groove and hidden chamber has a story to tell about our shared capacity to innovate. If this journey through overlooked history has reshaped your perspective on the past, we would love to hear which feature astonished you most. Share your thoughts in the comments below and subscribe to continue delving deeper into the enduring mysteries of our shared human story.